Hello, guys. Welcome back to Baby Boomer Doesn't Know How Technology Works, and we'll probably be talking for the next 10 minutes, only to figure out that he didn't record it and is embarrassed and has to do it again. Um, Hopefully this time does work though, because today we're going to be talking about Hess's law. Hess's law, at its simplest, the formal definition is that Hess's law states that the enthalpy between two sets of chemicals, i.e., the products and reactants, is the same. It states that the difference in enthalpy between two sets of chemicals, the products and the reactants, is the same regardless of how one set of chemicals is transformed into the other set. Um, what does that actually mean? That was a lot of mumbo jumbo, but here, maybe let me rephrase it like this. The difference in potential energy between two sets of chemicals is always the same regardless of how one got there. Regardless of how you got from chemical set A to chemical set B. That still doesn't make sense. Let me use an analogy. Um, the analogy would be essentially basically stating that, say you went from your home to your school, and say there was a bunch of different paths there. You could go, you could follow a direct path. You could take, you could go through the park or whatever. But it basically states that the displacement you have from you to your school is always the same, no matter what distance you actually traveled. So, say going by the park was a kilometer, whereas going straight was only half a kilometer. It doesn't matter that you traveled that full kilometer. The net displacement between your house and your school is always 500 meters or half a kilometer apart. That's the best analogy I can give. Um, Now, what? Okay, great. We have this statement, but what can we actually do with that statement? This means nothing. Now, the most common application of this is that we can actually manipulate things algebraically, and we can calculate the potential energy change if we know the potential energy change from one thing to another, the other thing to another, but we don't know from A to C. Say we know A to C, B to C, but we can't. But we don't know A to C. Well, we can go from A to B to C, and the potential energy difference there. It's like a loop. It'll always be the same. Um, Now, this actually turns out to be quite an important idea that it doesn't matter how you transform from one set of chemicals to the other, because particularly for those of you doing uh, high level chemistry, uh, you'll be encountering these things known as reaction mechanisms, and it's actually really important because it basically states that reactions aren't always for there isn't always only one step. Some reactions take a series of steps to get from one to go from your reactant to your product, and I think it's important to introduce this sort of idea now because and this is the perfect way to do it because that follows the law of conservation of energy. It doesn't matter how you go from A to B. The difference between the difference in potential energy between A and B is always the same. Um, and I think it's important because it opens your mind up to this idea of, okay, things don't necessarily have to happen in one step. They can happen in 2 steps or 3 steps or 10 steps for all that matters. But regardless, essentially, we can boil it down to three rules. Um, um, if you reverse a reaction, you flip the sign of delta H. If you multiply it by some sort of scalar constant, um, you multiply delta H by that same scalar constant. So in the example here, we multiplied everything out by 2, and therefore delta H doubles, right? It intuitively makes sense. You put in twice the amount of product, you get twice the amount of heat. You get twice the amount of heat, either gained or lost, depending on if the reaction is exo or endothermic. And likewise, for the reverse reactions, if going up the hill gains you a potential energy of, I don't know, 6 joules, then going down the hill must make you lose a potential energy of 6 joules. And similarly, if you go from here to here, you get that one. You release that much amount of heat, but it takes an input of that amount of heat to, form that. Lastly, if two reactions are added together, their delta H's are added together, and you find the delta H of the resulting reaction. This one, think of it akin to adding vectors. Not like in physics, but I mean in math. Uh, for those of you that don't take the new, they changed the math up this year and they removed vectors from half the goddamn thing. But in essence, here, let me draw a picture. I think pictorially it'd be easier to demonstrate. Say you had, here's vector 1, here's vector 2, and we know that the vector sum is something like that. Forgive me for not drawing, but V1, V2, and V3, and we know that V3 equals V1 plus V2, right? Because that's the net vector. All right. So now that that sort of aside is done, that hopefully the idea of that should make sense. And if it doesn't, I don't know. Rewatch the video a couple times; it'll eventually click in. Now, let's do a sample problem here because this video is honestly kind of short, and I need my AdSense revenue. I need to get past the 10-minute mark so I can get that sweet AdSense revenue, and get those $2 that I've been looking forward to. Here, so let's actually pick one here. So we know that N2 plus 2O2. Forgive my handwriting here because it's really shit. Is 2NO2, and we know that delta H equals. I'm going to round the numbers here. These aren't exact, but I'm going to round these numbers up just for the sake of my sanity here because I don't have a calculator on me and I'm too lazy to pick one up. And then we also know that N2 plus 2O2 can get us N2O4. Delta H here is 10 plus 10. Calculate for this reaction N2 N2O4. Now, what I would do is first note that anything that you have on both the product side and the reactant sides will cancel out. So, what if, say, we flip this reaction? We get 2NO2 gets us N2 plus 2O2. And then we did N2 plus O2, two of them, I forgot, gets us N2O4. Let's add those up together and see what kind of net reaction we get. Since these appear on both sides, we can, cancel that, cancel that, cancel that, and cancel that, and we get 2NO2 yields us N2O4. Perfect. And what do we know about the delta H's? We can add them up. Now, since we flipped this reaction, we should flip this on a delta H, so it would be minus 70 plus 10 equals minus 60 kilojoules. Now, the exact numbers in the notes aren't they aren't 70 and 10. They're 67.7 and 9.7. I'm too lazy to work with those numbers, so I just rounded it up to 70 and 10, just so it makes my head not hurt. The actual answer is probably in like 58 or 57. I'm too lazy to do the actual math, but here, you know what? Let's do the actual math. 17 to 58. It's 58 kilojoules a mole. So, who cares though? But yeah, that's that. So yeah, thank you very much for watching. Hopefully this thing recorded. So yeah, thank you.